Thank you for the invitation. So I will do a talk in two parts. The first part, I will talk more about physics and modeling, because with point vortices, I often have some questions about that, so I will try to convince you that the question is a bit complicated. And in the second part, I will present my work, mainly the work I did with Martin Donati on collapses of point vortices. I will start by presenting the quasi-geostrophic equations. The quasi-geostrophic equations are used to do weather forecast. So this is an equation for geophysical fluid mechanics to study the atmosphere of the Earth or the atmosphere of a planet. And mainly you have three main hypotheses. The first, that is that you concentrate on the scale which allows you to approximate the atmosphere by the half space. Okay, so you are working in R2 times R plus, and you also have a certain interval of time, which is normally 2 days. Otherwise, you need more complex models. And the assumptions you make on the physics is that you have the quasi-geostrophic equation is kind of perturbation of what is called the geostrophic equilibrium. Geostrophic equilibrium is a kind of zero-order approximation where you assume that the fluid is strictly stratified and that you have no evolution in time, no thermodynamical phenomenon, and in this case you have domination of the Coriolis effect. And so you have kind of trying to understand the geostrophic equilibrium to see the quasi-geostrophic, which is the perturbation of this geostrophic equilibrium. So mainly what you have is, you imagine in the center here, you have a gap of pressure, you have less pressure, so the particle of fluid tends to fill this gap and try to go to the center of this low pressure, but you have the Coriolis acceleration that makes the particle deviate. And when these two forces are exactly compensated, what happens is that the particle of fluid here are going to evolve in parallel to the isobar pressure, okay, the line of isopressure, and I will make circles around this pressure. This is the geostrophic equilibrium, and the quasi-geostrophic equilibrium is when you make the next order of the approximation, when you make this situation evolve. So mainly, what you do is that you is not strictly stratified, but that is quasi-stratified, so you allow small oscillations, small exchanges of matters between layers of fluids. And you also allow the pressure to vary over time, so you use the law of thermodynamics to make this evolution. Okay? And the last aspect is that you not only consider the Coriolis effect, but you also add the standard mechanical Galilean acceleration. So that's an example of what is called the Brund-Weissele oscillation, so the oscillations between layers of fluids. So here you have a small island, then you have the flows that arise here, and because of the perturbation, you start to have small oscillations, and this creates this kind of clouds you see here. So the quasi-geostrophic equations in the most general formulation is the following. So you have a vector, the macroscopic vector is purely horizontal. You only have the interaction between layers of fluid that appear here. This is the equation for the stream function, and you have this new term that appear that make that the interaction is given by this Brund-Weissele frequency, this Brund-Weissele oscillation. Okay? And the quantity that plays the role of the vorticity for quasi-geostrophic equations is the quantity called the potential temperature, which could be seen as the temperature that would have the fluid if the exchange of temperature are neglected. And you have this transport equation that okay. And you can reconstruct, so you have this trace equation that gives you the potential temperature at time 0, because this is potential, so you need a reference. And you reconstruct all the potential temperature with this thermodynamical equation. Brund-Weissele frequency is data, so you need first to make some measure to understand the mass of air, and then when you have it, you can solve this equation. If you take the limit n going to plus infinity, you remove the between layers, so you recover the stratified system, strictly stratified system. And if you, on the contrary, take n going to 0, you will remove what is called the Taylor-Fluidman theorem, which is the case when you have 0 stratification. Okay, so this is an interpolation between both. This interpolation is made by. Okay. So in the case you have a specific structure for this Brund-based oscillation model, n square here, if you put this choice particular, then you see you have an equation which is the equation that appears in Caffarelli-Silves theory. And in this case, you have a Dirichlet-Tuneman operator, which is in the plane, the fractional operator here that we saw in the previous presentation. So you can, in this particular case, rewrite this system as a purely two-dimensional equation. Okay, and this is what we call the surface quasi-geostrophic. What is nice to do is to use the green function of the fractional Laplace operator here that I wrote GS. And in this case, you can write this as a single equation where V is given explicitly using this non-local operator on theta. Okay, and you can reconstruct V with this operator. So this is the equivalent of what is called the BiotSavart law for Euler 2D. Okay, this is the fractional BiotSavart law in the plane. So I put this this graph. So this is a measure of the Brund-based oscillation. This is to give kind of what it looks like in the scaling. So we study always n squared, not n. It's better to have n squared, and the scaling is 10 minus 4 second minus 2. Yes. So if you want to say the period, typical period is 1 minute or 10 minutes to have an oscillation. So it is much slower than the sound, for instance, but this is still the fast variable because you want to know the weather tomorrow, the day after tomorrow. So this is the fast variable. So that's why it's just a derivative equation. I want to emphasize the fact that here the n square is negative, so this corresponds to a frequency that is imaginary. So it means that the cosine becomes hyperbolic cosine. So this is the signature of a layer of fluid that is not stratified. Okay, that's what it means. And this is well known. This is the stratosphere. This is the mesosphere. So this is the signature of the passing from one sphere to the other sphere. So how do you predict the weather using this equation? So what you know is that at first order, the fluid is following the line, which are the black lines here, the green black lines, which are the pressure lines. Okay, so the fluid is going this way, like this. Okay, turning around the low pressure. But to have a better model, people who are doing weather forecast, they add this kind of lines. These lines are the regions where the approximation by quasi-stratification is false, so you have a vertical phenomenon. And this is how they predict the presence of clouds. So for instance, the red line, you have a hot mass of air here, which is pushed by a cold mass of air, so in this specific kind. No, that's the contrary, so it's cold here and hot here. And the hot pushes the cold one. Here, that's the contrary, it's a cold mass of air pushing a hot one. And here you have the situation where the hot mass of air is pinched between two cold mass of air, and the air goes upwards and create big clouds and lots of rain. So here you have a big storm. And what you know is that this big storm on Norway is going to go into Finland following the lines of phase pressure. Okay, this is how we predict the weather. About the point-vortex system. So you just have an equation which is a transport equation, and you wonder what happens if you do the approximation that at time t equals 0, the distribution is from the sum of Dirac masses. So in this case, you have the evolution of the Dirac mass. So the Dirac mass itself with the BiotSavart law creates a field, a velocity field that turns around the Dirac mass, and the intensity of the velocity field blows up in the neighborhood of the Dirac mass, and the other Dirac masses will turn around this Dirac mass according to the equations I'm going to write later. So there is a question about, is it a relevant model to have this approximation by Dirac mass, which is approximation by vortices? So I put here two numerical simulations, which are not completely comparable, but this gives a bit the picture of the debates on this question. So I will try to convince you that these two pictures are very, very different. So this one is made of small vortices a bit everywhere that we see here, this kind of rounds that we have. This is for Euler in dimension 2, so you don't have a fractional Laplace operator, but a full Laplace operator. And what you have is lots of vortices that evolve in kind of a soup made of filaments of vorticity around them. Whereas in this case, this is the contrary. You don't have lots of filaments, you have very small filaments, but you have lots of multi-scale vortices. You have lots of big and small and very small and very, very small vortices. So you may think that this is better approximation for SQG, but Ludovic is a bit more complicated. Because if you take a kind of ellipsoid approximation or an ellipsoid vortex, so the evolution for the Euler to the equation will make this kind of filamentation appear in the equation. You will have this that are created. But for SQG, you will also create filaments. But what happens is that since the singularity of the kernel, which recreates the vorticity, is very much higher, when the filaments are thin enough, then you have this shedding and stretching phenomenon, where the filament turns back into smaller vortices. Okay, so you have this filament, and then this filament creates smaller vortices. So you have a creation of multi-scale structures from a large-scale initial data. Nevertheless, so this is a slide that was given to me by Peter Hein. There is a phenomenon that they studied because of this big bushfire you had in Australia a few years ago, 2020. This creates a big cloud of dust, the size of Australia. You imagine it's a big cloud, and this big cloud of dust was absorbing the rays of the sun, and it was acting like a source term in the equation. So it was preserving these structures, and you had a very long-term localization of the vorticity. So the approximation was good. This was very long-term because it started 24th of January and 4th of March, it was still concentrated. So you do have physically structures of long-term concentration of vorticity. Mathematically speaking, you have several results. For Euler 2D, this is something a lot studied. So you try to make an initial data that is concentrating in one or few points, and you try to understand how long will it stay concentrated. So you have both desingularization, so you approximate the Dirac mass, or you have only localization, and you try to understand how long does it stay localized. For SQG, because of the fractional nature of the equation, this is much more difficult, but you do have a lot of literature on these problems. There is another kind of literature that I don't understand very well, but so these are the paper I managed to understand the statement of the theorem once in my life. So what they do is mean field limit. So they put lots of point vortices with vanishing vorticity, and they try to understand what happened. And what they show is that mean field limit for this equation exists, and you can obtain back the original PD equation as mean field limit of small point vortices. So you can see this equation as infinitely many small point vortices. This makes another reason why this is interesting to study. Yeah. Another interesting fact about point vortices is that this is quite used for studying more complex phenomena, like if you want to study nearly parallel vortex filaments. I saw works about hurricane center dynamics using point vortices, so this is quite standard to use. So now we are doing some math. The point vortex dynamics, when you have either the Euler or the supposed Quasi-geostrophic equations, you can always rewrite them in this more general context, which is alpha point vortex model. So you have a kind of kernel G, and you take the grad perp in the plane, so you take the gradient and you rotate of angle pi over 2, and you have this coefficient, which is the vortex, the circulation of the vortex. Okay. So you can this is the general case. You take alpha equals 1, you have Euler. If you take alpha between 1 and 3, you have G, SQG, general Quasi-geostrophic equations. And you have the 1/2, which is critical, as you know, when you take alpha equals 2. And if you take your favorite theorem for ODE, you know that this is well defined in time as long as the distance between vortices remains positive. So the question is, what happens when the distance is no longer positive? So this is collapses of vortices. So there is also something that the regularization of this kernel for radius lower than epsilon to write the theory, which we have without this problem of the first point to remark is that you have a Hamiltonian property, because if you write the dynamics of a vortex times its circulation, you can see it as the orthogonal gradient of some Hamiltonian, which is written this way. So you have lots of preserved quantity that are going with Hamiltonian formulations, such as UV theorem, for instance, and Hölder theorem. I will mainly use this preserved quantity because if you have what we call non-degenerate hypothesis, which is the sum of the AI that is not zero, this is the preservation of the center of vorticity of the system. The non-degenerate, so in general, we work with this general non-degeneracy hypothesis, which is that any cluster and subclusters of vortices is never neutral, which means that the total sum of vorticity is zero. So this is the generic case, of course, in terms of topology. But this allows you to define the center of vorticity, which is constant of the. Of course, there's a.
Who is the AI?
It's the intensity of the vortex, the circulation. The problem is that neutral systems have a physical meaning because you have preservation of vorticity in fluid mechanics. So if you have a fluid at rest, for instance, and you do a perturbation, you expect that this perturbation will be vorticity preserving. If you go canoeing, for instance, you will see the apparition of two counter-rotating vortices and this kind of stuff. But this is not too bad because we know how to create a system that satisfies this physically. So the first property I will present to you is the uniform bound property, which is the following. So you consider the point-vortex dynamics under this non-degeneracy hypothesis with a kernel profile of alpha with a regularization. Then you can prove that the trajectories are bounded on an interval of time, and that the bound you have is independent on the singularity of your kernel, on the regularization you make, and also independent on the initial data. So how do you make this? You consider a situation where you have all the vortex inside some ball, for instance. So case one, they stay inside the ball. Well, so you have closure theorem, you're happy. Case two, they leave the ball collectively, and they go very far collectively. Then you have preservation of the center of vorticity. So you cannot preserve the center of vorticity, which is the barycenter of the system, and go to infinity together. It's not possible. So you have a third choice, which is you leave the ball, but separately. You have one cluster here, one cluster here. And then you're happy because they are far from each other, so it's just a Lipschitz interaction between both. So you can apply recursively this theorem to this cluster and this cluster. So if you can do a recursive argument, and if you compute explicitly the best constant you have, you see that this constant does not depend on alpha, epsilon, and the initial data. So this was done first by Marco Pulverenti for Euler 2D. The subcritical case was handled by Hölder, and I did the general case. If you do neutral systems, but you have the total sum that is zero, but not the sub-sums, you can do the same kind of study, but you only study relative dynamics, not exact dynamics. There is also results for improbability of collapses, which is something important for people doing mean field by approximation by infinitely many vortices. And in this case, you have to restrict the analysis to alpha equals 3 because you have a critical exponent that appear. And in the case, you can prove that the set of initial values that lead to a collapse in final time is a set of Lebesgue measure 0. What you do is that you make a kind of energy that blows up in the presence of a collapse. You integrate in space and time, and you do a Chebyshev inequality. And when you study this inequality, using the fact that you have a UV theorem, you can estimate the size of this set. So this has been done by the same list of others. Marco and Pulverenti for Euler, they found the main arguments. Geldoser Romito made alpha between 0 and 2, but they had a problem with the criticality that appears from fractional Laplace operator of exponent R. And I managed to get rid of this problem making some compensations in the integral. But I still have a problem for alpha plus 3. And the case of when the whole system is neutral was also. And at the very same moment, Martin Donati, which became my co-author now, did the case for Euler in smooth bounded domains. Here you have to study precisely what happens when a vortex collapses with the boundary of the domain, which is not that simple to see. There is another theorem that I presented to you, which I will spend maybe a bit more time to explain it, which consists in the specific case of the Euler point-vortex system, so alpha equals 1, always under this non-degeneracy hypothesis. And in this case, you can study the dynamics until the time of collapse, and you can prove that you have convergence of the dynamics. This is not clear because when you have the derivative in time that blows up when the distance goes to 0, so you have the velocity that goes to infinity, so it's not clear a priori that the position converge, but you do have this integrability property. So the proof I had was inspired from the works by Gerald Metz for the binormal flow, which consists in studying first the distribution of the point-vortex system. So you find intensity, a Dirac mass on the vortex. This is a distribution that evolves in time. And I compute the evolution in time of this distribution. So I just here write what it means. I put here the point-vortex equation. Then I do the law symmetrization of the sum. Okay, I switch the role played by I and J here. And at the end, I make appearing this difference between grad phi at xi and grad phi at xj. And this scales like 1 over xi minus xj. So this is something that is like, how to say, something mean value theorem. So you can down all this term directly by the L infinity norm of the second derivative, of the derivative of the derivative of phi. Okay? So you have this that converges as a distribution in D prime, and more precisely in the dual space of W2 infinity. So how do you conclude? Here, you have convergence of the distribution. And what you can do when you use this non-neutral cluster hypothesis, you can use it to prove that for a given point vortex, the set of adherence points for this vortex is necessarily included in the support of the limit distribution. Why? Because you have non-neutral cluster hypothesis. So when you take one point, you put a test function around this point. When you have vortices that pass through this, in the support of this test function, you will measure something which sum is not 0. So you will measure something. And this gives you, when you rephrase it properly, it gives you that the support of the limit distribution contains all the adherence points of the vortices. But there is also a result, since you are bounded, which tells you that if you take a continuous system bounded, then you have, of course, existence of an adherence point, but you have better, if you do topology, which is that the set of adherence point is a connected set. This is a consequence of continuity. So you are contained in the support of the limit distribution, and you are connected. So the set of adherence points is something that you expect to be a single point. But on the other hand, you can prove that the limit distribution itself is the sum of Dirac masses. So you are connected. So the set of adherence points for a vortex is connected, contained in a finite number of points. So it's a single point. It gives you the convergence. The weakness of this proof is quite clear. The first is that it's not general. It's alpha equals 1. We need this to make. And also, when you see the proof, you remark that you understand hardly anything about the collapses of point vortices. You just create a topological obstruction of non-convergence. That was a bit the point of the question. I just write that you can do the same kind of work for bounded domains. So you create the distribution, and you can have convergence on the points when the adherence point belongs to the interior points, because on the boundary it's more complicated. Okay. So this is the main part of the work I did with Martin Donati, which is the following. So the first thing to say that collapses do exist, otherwise this study is not interesting, of course. So you have lots of results. So for Euler 2D, this is only self-similar for the three-vortex collapse, which is easier to understand. You have only self-similar collapses. But for SQG, this is proof that there exist non-self-similar collapses for the three-point-vortex system. And the self-similar case for other values of alpha were obtained independently here. And you also have Euler 3D plus Lipschitz term, which is obtained by these authors, which implies the existence of vortex collapses in bounded domains. For existence of n vortex collapses, I have not seen results, except some numerical investigations, but not results from that. So the theorem we are proving is the following. So you consider a general point vortex system. So this is an alpha. And you work on the non-alpha cluster hypothesis because you need to exploit precisely this, very precisely this non-degeneracy. And you have dynamics, which you assume that it is well defined in some interval of time 0t. And then you have this Hölder regularity property that we proved, and the constant of Hölder does not depend on the initial position, and does not depend on t. Okay. So in particular, this gives you, of course, the convergence in presence of collapse. So if you have a collapse at time t, you can prolong, you can continue the trajectories until this time t, but this is of course much better because Hölder regularity is not only a continuity. One point of view in this result is making the link with the uniform bound theorem that I showed you before. In some sense, this is the explicit computation of the dependence in time of this constant. This is a way to see it, but this is better. I just wanted to say that I had this result for n equals 3, but the argument I had was purely energetical, which does not generalize to higher. A bigger number of vortices, so you do have to make a precise argument. But the argument is inspired from the uniform bound theorem, which consists in studying this kind of separation of clusters. But here, to have this bound, you need to be much more precise on this separation of clusters. You must understand the scales in space and the scales in time at which this separation of clusters occurs in your dynamic. So yes, I state also the theorem for Euler 2D in bounded domains. I will not prove this fact. I will only explain the variations that are needed to obtain this theorem. Similarly to the convergence theorem we proved before, you have to make this difference between two kinds of vortices. You have the vortices that collapses with the boundary and the vortices that collapses far from the boundary, but stay far from the boundary, because this is not the same story. If you remain far from the boundaries, if you are not in this set, then you can do this argument similar to the previous theorem, and then you have this Hölder regularity, which is the square root, because we have the regularity 1 over alpha plus 1, here alpha plus 1, so this is 1/2 Hölder regularity. If you collapse with the boundary, then you can make some variations of the arguments we have to have the convergence not of the point itself, but on one component, the normal component. So if you consider the distance between the point and the boundary, then this distance itself is Hölder continuous. But you won't know if you collapse at one point of the boundary or if you make turns or oscillations or complicated stuff. But you still have, so there is still a study to do for the other component. So let's switch to the proof. I introduced the degeneracy parameters, which are the following. The most important is this one. You can reformulate the non-degeneracy hypothesis that we need as the fact that this quantity is positive. Okay, we never have any subsum that equals to 0, and we also need this The first lemma to prove our result is the following. is to control the distance between one vortex and the center of vorticity of the system. So this is the general statement. If you have a family of points in RP and some multiplicative scalars, such that you can define, of course, the point, the barycenter, then the barycenter here, you can control the distance from one point to the barycenter with some constant here making appearing these degeneracy parameters times the maximum distance between points. So when you see this lemma, you understand why you can expect convergence results. Because what you have is that this guy is slow. This is a conserved quantity, so he will not move a lot during the dynamics. And if you consider the whole dynamic, it does not move at all. Okay. So this guy is, we don't know what he's doing, but we know that if he is close to other people in the cluster, then he will not go far from the slow person. Okay. So if the people are close, they're about to collapse, then you can expect them to be close to someone who is slow. Okay. So here you have the main idea of the proof. But the proof is very easy. Okay. You just write the definition of B, then you have a triangular inequality that appears, and then you have the two parameters that you need that are here, and then the max. The proof is not interesting. That's the philosophy of the lemma that's relevant. So then the question is to understand how to deal with clusters of vortices, because if you understand well the size of the vortices, you can control the dynamics with the previous lemma. So it's something important. So what we use is the Ball's lemma that we saw in different formulation elsewhere, which is the following. You take n points in RP, and you need two parameters, a parameter epsilon, a parameter kappa, and you can show the existence of some parameter delta and a subset of indices, such that delta is controlled by epsilon from below and by some factor here times epsilon from above. So this means that delta is not too. If you take kappa close to 0, you have something bad. So you have to adjust kappa at some moment in the loop. The second point is that you have the union of all the balls of tile size epsilon that are contained in a smaller union of balls with a bigger radius. Okay. And the third thing that you want is that the points that do not belong to the same bigger ball are at big distance from each other. So the picture is the following. You have some people represented by these diamonds here, black and white. Around this diamond, you make a ball of size epsilon, which is the balls that are here. Okay, and then you pick one particular guy and a ball of size delta here, and one particular guy, a ball of size delta, such that all the person here are inside balls of size delta, and you have a big distance between these two balls of size delta. And this is the way you can create your clusters with these two parameters, epsilon and kappa, that will be efficient for you. The proof is iterative, so you take the first set Q1, which is everybody, and delta 1 is epsilon. So you always have property 2 that is fine in this case, and 1, of course. But maybe it is not satisfied. You don't know. So if it's not satisfied, then you build iteratively the decreasing sequence of set Qk with an increasing parameter delta k at every step. And you will have property 1 that holds all the time because you will do a finite recursive argument. And property 2 is always satisfied, but maybe 3 is not satisfied. But if property 3 is not satisfied, it means that you have 2 points, xi, xj, in this qk, such that the distance between both is not property 3. Okay? And what you do is that you define your new set at the next step by removing one of the 2 persons and by increasing the size of the ball of the delta. And since you increase the size of the delta, the xj will be in the same ball of size delta k plus 1 than xa. Okay. That's what is written here. Simply triangular inequality gives you iteratively the inclusion of this union of ball. And then since you are decreasing the number of people inside your set, then after n step, at most once property 3 has been obtained, and then this gives you the results of the. So the corollary that we have, which is easier to manipulate, is the following, but it's just a rephrase of the ball lemma. You take n points in RP and a kappa, parameter small, assume small, and the distance d. Then you have a small delta in an interval that is of size d plus some parameter, and the partition of the set 1n such that people that belongs to the same element of the partition are closed, and people that belong to a different point in the partition that are far, which is the clusterization we need for the construction. With this way to separate points in different clusters in the space, we can prove this general proposition which help us obtain the result. We take xi, a family of n different points in RP that evolves in time, and on some interval of time positive. I consider this coefficients that satisfy this non-neutral cluster hypothesis, the non-degeneracy that I need. I make this general assumption. I'm not doing point-vortices here. I'm just doing general dynamical systems. I say that when I have this barycenter associated to this coefficient for every p included in the subset, I make this assumption, which is a slowness assumption. I say that the barycenter is slow, meaning that here I have this estimate. Okay, so I sum on I in p with j outside p. Okay, and recall that I'm doing a good separation. So it's here that I will use the fact that two clusters are well separated. And if I assume that the center of vorticity is slow, meaning by what is written on the board, then I can prove that I'm going slowly. I would say this is not exactly what it means, but I say that if I don't have enough time, which is this, then I cannot go far. This is the meaning of this proposition. So if I am slow, if I don't have enough time, then I cannot go far. This is the resume, the sum up of this proposition. Of course, this is more precise because this is quantified. I know the interval of time on which I cannot go far. Okay. Morally speaking, the quantity eta here is a distance because we see here, this is a distance. So what is written here is almost the Hölder regularity that I stated. Because what I will do after is that I will write the negation of this, since I have a collapse. So I will write the negation of this, and this will be 1 over alpha plus 1, exactly what I say. So this is almost the Hölder regularity. Idea of proof. What we've done is we use the clusterization we have, we will use it at fixed time, and we try to understand how much does it take to have far away clusters that merge. So for that, we need to build an iterative number of partitions for some parameters q, like this, and also a sequence of parameters delta and sequence of times that are satisfying a list of properties that I will show to you. The first one is that we want this new partition to be a subpartition of PQ. Why? Because it is to study the case where you have a cluster that divides into two smaller clusters. The second property that you want is the following, which is that inside the cluster, at this time TQ, you are close to each other. The third property you need is that when you belong to two different clusters, then you are far from each other. The fourth property you need is to control, this is very important, this parameter delta Q, depending on some parameter kappa, some parameter S, or everywhere. But what is more important is that you have this eta. I told you that this eta must be understood as a kind of distance inside the cluster, the mean distance inside the cluster. And the fifth property that you need is that inside the full interval of time between the cluster you have and the cluster at next time, then people do not move too much. Here you will use the first lemma I showed you. Okay, inside my interval of time, people will be close to their center of vorticity, which is slow, so they will remain close to this center of vorticity. So I can extract a whole interval of time where people remain close to their initial. And the last property I need is that on all the remaining interval of time, I remain close to this thing. Okay. So how from this construction, iterative construction, what I do afterwards is that I take all the interval of time from big T to T1, and this gives me the interval of time that is in the proposition. Okay, so this is the construction that makes everything work. The corollary is the following. So this is simply the negation of the proposition. If I have a collapse, then the interval of time that I have is bigger. So this is simply the following. I assume that I have a collapse. Then I know that the initial distance was smaller than the interval of time. So this is exactly the rewriting of the proposition I showed you. Okay. So this is not exactly yet the Hölder regularity we want. This is quite general. This is not point-vortex yet. So the first element to see is that we have a theorem for uniform bound dynamics. We know that the dynamic stays inside some big ball. So I have the existence of an adherence point. And what works is that I can define a bigger system where I take the first points as being the moving points, and I add inside the system the limit, the one adherence point of the system. So I consider a bigger system than only point vortices. I take this system and the expected limit for the point at time big T. And since I proved a very general proposition, I can apply this proposition to this bigger system. And here, what I will have zeta I of t minus zeta j of t, and I will take zeta j to be this person. So when I apply this general theorem to this bigger system, I exactly have xi of t minus xa of big T. This argument is specific to the point-vortex system because I can extract the point here. And this is almost a Hölder regularity. The one weakness is that here this is the final time, but Hölder regularity is not the final time. You need to have T1, T2 for all T1, T2 small enough, this kind of thing. So this is almost the result. So to conclude the Hölder regularity here, the observation is the property of time big T. Because I make all the construction as if big T is the time of collapse. But in the proof, when you watch the proof properly, you see that at no moment in the proof, I use the fact that we do have a collapse at time big T. Actually, I do not use the property of big T. So I can choose big T freely, just the final time, but not the time of collapse. So since big T is free to choose, actually, this is xi of t, xi of back t. But I can choose big T as being the time T2 I wanted. So this is T1, T2. So this is actually Hölder regularity because I never used the property that we do have a collapse at big T. So this concludes the proof. I will just say that in bounded domain, it's a bit more complicated because you have the influence of the boundary. So as long as you stay as long as you stay far from the boundary, this is just a Lipschitz interaction, so this is okay. This is not easy, but this is okay. You can deal with it. From the influence of the boundary, you have a problem. You want to do the same trick. You say, oh, I add the boundary as a kind of extra vortex in my dynamics. I just said it does not work. So we need to prove a more general proposition. And so I need a family of n different points in RP that evolve in time and satisfy this kind of non-degeneracy hypothesis. And I need a slowness hypothesis. I have this term that I already had. I have constant. I need to have an extra term here. Okay. which moves many things in the proof. And for this more general proposition with this extra term here that models the interaction with the boundary, you need to have a special cluster of vortex, which is the vortex of points that are close to zero, that plays a specific role in the proof, so you have to move several things, but you can have this more general result with this extra term. And if you can have also add like some points in the plane where you have this kind of singularity, as long as, of course, these points are discrete in the plane, you can make this small general statement, which is that if you are in a too small interval of time, then you cannot collapse using this slowness hypothesis. Okay, I finished.